Hey everyone, thanks for having me. I was thinking when I was sitting backstage, this is a week of firsts for me. First time lead falling, first time bouldering outside. If you don't know what that means, don't worry about it. But so I was ready for a work first time. My work first time today is standing in front of a presentation that is bigger than I am. So yeah, my name is Aimee Barciauskas. I work at Development Seed. I'm a data engineer there. We work with NASA to act as data providers, as well as we work with organizations like the World Bank to build applications that power decision makers.
That's the laser.
That's the laser, OK. Oh, big green button, OK. So when we talk with government data users, we often hear the phrase, it ought to be easy. And we're excited to be here today because we agree. The Mapbox mindset is all about being able to provide data that is easy to access, easy to use, and enables decision makers to make decisions faster. So what does easy look like? And more importantly, what does easy and impactful look like? We built a tool called the Hurricane Intensity Estimator in collaboration with the National Hurricane Center at the University of Alabama, Huntsville. This tool uses neural networks and GOES satellite imagery to enable real-time decision making or real-time predictions of hurricanes as they happen. And this is impactful because if you can have real-time prediction of the intensity of wind speeds, which is the best predictor of the destructive power of these hurricanes, you can set out your response teams faster. And it builds and enables you to set out those response teams and the possibility to save thousands of lives. In 2017, hurricane disaster relief cost the U.S. Government $280 billion. So how did we do it? So historically, meteorologists have been using a technique called the Dvorak technique. So this is your science trivia for the day. So the Dvorak technique basically uses subjective pattern recognition and applies a set of objective rules to those patterns enabled to estimate hurricane intensity. And this is cool because we hear, pattern recognition, a great training data set with these labeled satellite images. We can use machine learning. But for a long time, we didn't really need machine learning because imagery was the bottleneck. We only had so much imagery. That's not true anymore. Now our cup runneth over. We have too much data. So with the GOES-16 satellite the GOES-16 satellite, we have data that can be made available every 30 seconds, providing this near real-time predictions. So we worked with the NASA's Marshall Space Flight Center. We developed this hurricane intensity estimator. It uses a linear convolutional neural network to provide these predictions in near real time. So how did we do it? We also used AWS. So this is basically what our process looks like. We download the GOES. We monitor the INVEST area, which is basically the hurricane weather system. We download the GOES image that's associated with that weather system. We predict the wind speeds and write to the database. And boom, impact. So that was easy, but that was just one application. How can we replicate this? How can we keep up with all the data? This is just one data set. There's so much data out there that we can use. How can we make easy and impactful possible across domains? So we've already talked about how humans and AI can work together. But another thing we want to talk about is a new way of thinking about data. So we're working with NASA, ESA, and USGS to revolutionize Earth science by providing cloud-optimized geotiffs and ARDs out of the box and making those data formats available on the cloud publicly. NASA's had a commitment to open data since 1994, committed to opening up all of its data. However, as you may be aware, NASA's Earth Science Department is going to be experiencing a hockey puck hockey stick amount of growth in its data, exponential growth in its data in the next 5 years. Specifically, the NISAR mission that's coming up is going to be ingesting and processing petabytes of data a day. And this commitment to open data is becoming much more difficult, if not impossible, without the cloud. So typically, if you see on the left and the right here, typically NASA has been providing data in these distributed active archive centers, on-premise data, these on-premise data stores. That's not going to work for this new level of data. So they've invested in a new piece of software called Cumulus, which Development Seed prototyped and is continuing to develop with the Cumulus core team. So Cumulus is basically a piece of software, a piece of open source software. You can check it out on GitHub/NASA/Cumulus. And it is basically the tool that they're using to ingest data, publish it on the AWS cloud. And what's cool about Cumulus is it can also be used for things like generating higher level products that can be used for analysis applications. So creating those cloud optimized geotiffs, creating those analysis ready data sets. That's some of the things that we're working on in our projects that use Cumulus, including the hurricane intensity estimator, which also use Cumulus, to basically create these data sets that are science ready data sets, application ready data sets. So now using cloud-optimized geotiffs and ARDs, I don't just need a copy of the Landsat archive and my own supercomputing cluster to do research on decades of Landsat data. I can just grab the pixels I need. I can drop imagery directly onto mobile applications as it comes off the satellite. I can create image chips without an army of grad students. I can build collaborative science tools that allow scientists to work together on huge data sets, replicate results, and automate the production of future insight. And this last bullet is something that I'm actively working on right now. There's a project that we're working on in collaboration with NASA's JPL and the European Space Agency called the MAP. It's the multi-mission algorithm and analysis platform, the MAP with 2 A's. And it's basically exploring this idea of what does open science look like on the cloud? How can we get scientists to work together on the cloud to make their data reproducible and shareable, make their algorithms shareable? Cool, so faster applications. Now we can build applications easier. We can make them, we can focus on the impact and not the building. And we do this with clouds, ARDs, and Mapbox. And one example of this is this application we built called LibraLive. So LibraLive is built using the Mapbox API as well as some other open source tools that came out of Mapbox, and it's using dynamic tiling. So as you scroll around on the app, you get these dynamic tiles coming back, as well as what you're seeing here is basically real-time road detection. So a road detection model that was built at Development Seed is being displayed in real time as the user pans around. And this was also built with the user in mind and mobile first, in that it's supporting this vision of, what does easy look like by enabling the user to, it's integrated with Amazon's Alexa. So basically, when you talk to the app, you say, show me roads in Seattle, and this is what you see. And it was built in 1 week. So AI at scale, it's not just hurricanes, right? We're applying these same ideas using the Mapbox API, partnering machine learning with human expertise to do things like detect the power grid in Nigeria with the World Bank, locate schools in Colombia with UNICEF, and map roads in the Philippines. And a Mapbox API is at the core of all of these applications because it makes our lives easier. So finally, what do I want you guys to take away from today? What does the future hold? I'm not superstitious, but we think that the future looks like partnering human expertise with artificial intelligence. This can expand the scale of analysis and impact. Providing open and analysis-ready data supplied by organizations like NASA, ESA, and USGS. And user-driven tools like the Mapbox API. If you are interested to learn more, please check out our website, developmentseed.org/projects. You can find specifically links to the hurricane project that I talk about, which has links to the documentation, the methodology, and the tool, the live tool, which is hurricane.dsig.net. Thanks.